Hello everyone, this is Dr. Carlos Carrera Zarco. Welcome to this new session of your module in Big Data and Business Analytics. In this session, we are going to start with some basic concepts to understand data analytics. So this session will be focused on essential maths and statistics for data science. Here you have the main learning objectives for this session. The first one is to be aware of which are the main mathematical concepts which are involved in data science. Also, you will gain knowledge in which are the statistical areas that are pretty connected with data analysis. You will understand which are the key differences between descriptive statistics and inferential statistics, and you will start your learning path about descriptive statistics. In this first part of the session, we are going to talk about some key mathematical concepts which are connected with data science. Most of you must be familiar with these concepts, but I will refresh the fundamentals of these concepts, which are going to be basically vectors and matrices. Vectors and the vector spaces are in the foundations of linear algebra, and linear algebra is going to be used in many manipulation data scenarios. Vectors describe spatial lines and planes that enable you to perform calculations to explore the relationships in multidimensional space. Vectors are usually named as lowercase letter, like for example here, V, with an arrow above them. Here you have a vector in a two-dimension space, while here you have this vector W, which is a 3 dimensions vector. The vector itself consists of a set of values that describe a direction or amplitude and a length or magnitude. To calculate this length or magnitude, we can treat the vector as the hypotenuse in a right angle triangle, and then apply the Pythagoras theorem. Calculate the direction or amplitude is going to be a little bit more complex. You can calculate this value, the direction or amplitude represents here as theta, as the inverse tangent of the opposite over the adjacent, or y over x. We can do several operations with vectors, and they are quite straightforward. The addition is basically to sum the vectors component by component. Here, this vector, which represents b plus w, would be 3 plus 2 equal 5, 1 plus minus 4, that would be minus 3. You can see graphically how we can represent and obtain the vector that represent the addition of two different vectors. For subtraction, basically we follow the same procedure, but obviously subtracting component by component. The scalar multiplication is also very easy. Basically we are going to multiply each component of the vector for the scalar. The dot product is also quite easy, and this will produce a scalar. You can see here how to calculate the dot product, basically to multiply component by component and then to sum both components. The cross product of two vectors will produce a new vector that is perpendicular to the original two vectors in three-dimensional space. So only really makes sense when using three-dimensional vectors. To calculate the cross product, you need to calculate the individual elements of the resulting vector. For the first element, we will forget about the first element of these two vectors and we will multiply this way: 2 for 1 minus 3 for 2. For the second component, we will forget about second component of both vectors and we will multiply again this way: 3 for 3 minus 1 for 1. And for the third component, we will forget here about these components and we will multiply again doing this cross: 1 for 2 minus 2 for 3. And we will get the vector that represent the cross product of two vectors. Here you can see graphically its representation. Now I'm going to introduce some basics about matrices. Overall, a matrix is an array of numbers that can be arranged into rows and columns. And we usually designate a matrix with a capital letter. Here we have two matrices, matrix A and matrix B. Both have two rows, as you can see, and three columns. It's very easy to add or subtract matrices of the same size, okay? Simply by adding or subtracting the corresponding elements in the two matrices. Here we have representing A plus B, and clearly we are just adding 3 plus 2, 5 plus minus 2, 1 plus 4, etc. Also, we can multiply matrices. The scalar multiplication is quite straightforward because you just need to multiply each element of the matrix by the scalar multiplier. Here you can see in the example A for 2. Dot product multiplication is easy too, but it requires two matrices in which the number of columns in the first matrix is the same as the number of rows in the second matrix. So we can multiply A for C because the number of columns in A is 3 and the number of rows in C is also 3. And here you can see in a simple example how we can multiply two matrices. Basically, we will multiply one by one the elements of the first row in the first matrix by the elements of the first column in the second matrix. In that case, 3 for 2, 5 for 1, plus 1 for 3. And here we have the first element of this dot product for two matrices. We can also implement matrix division, and we will follow this rationale. To divide for a number is the same that to multiply for the inverse. So to do matrix division, we will follow this rationale. Here we want to divide A by B. So we will have to obtain the inverse matrix for B. To obtain the inverse of B, we will apply this mathematical formula. Once the inverse of B has been obtained, we just need to multiply A by B exponential minus 1, which is the inverse of B. Matrices are very useful to solve systems of equations. Here you can see a very easy example on how to represent a system of equation with matrices and how to solve the system by obtaining the inverse of the coefficient matrix and multiply by this matrix which represent the number which are after the equal. This is a very straightforward method to solve systems of equations. Okay, in this second part of the session, we're going to introduce some basic concepts of statistics. And the first question that could come to our minds could be why to use statistics. Well, we have here a number of good reasons that justify the use of statistics in data science. With the use of statistics, we can summarize our raw data by using basic descriptive statistics, normally univariate analysis. We can make group identification, clustering. We can find differences between groups in our data by using bivariate statistics. We can find relations between different variables by doing correlations. And we can predict outcomes, for example, with the use of regression analysis. Well, from the very beginning, it's important that you distinguish between the two main areas of statistics. We have descriptive statistics and inferential statistics. The descriptive statistics is more connected with collecting, organizing, summarizing, and presenting the data, while the inferential statistics will try to infer information from a sample of a whole population. These methods are good for hypothesis testing, to determine relationships between variables, and to make predictions. Here you have some basic differences between descriptive and inferential statistics. Usually, the descriptive statistics is to work with a smaller dataset. Processes are simpler than the inferential statistics processes. The results represent the entire dataset because we are working with a reasonably small dataset, while in inferential statistics the results will represent a portion of the population, a sample. But as I said, you can use that sample to deduce information about the entire population, obviously considering some amount, some degree of uncertainty. And obviously the error involved is usually less in descriptive statistics than in inferential statistics. Before going further with descriptive statistics, it's important that we understand the different types of variables that we can use in statistics. We need to know which types of variables we are going to use in order to choose the appropriate statistical test and to read the results of our study correctly. In general terms, data is a specific measurement of a variable, and this is the value that you record in your data set. We can find two main categories for data in statistics: quantitative data, which represents amounts, and categorical data, that represents grouping. Obviously, a variable that contains quantitative data will be a quantitative variable, while a variable that contains categorical data will be a categorical variable. Now we are going to introduce the quantitative variables. When we are using quantitative data, the numbers that we are using represent real amounts that can be added, subtracted, divided, etc. There are two types of quantitative variables: discrete and continuous. Discrete variables can count individual items or values, like for example the number of students attending this session, while continuous variables measure continuous or non-finite values, such as physical magnitudes, for example distance, time, volume, age, etc. The categorical variables represent groupings. Sometimes we can find them recorded as numbers, but these numbers represent categories rather than an actual amount of things. We can distinguish mainly three types of categorical variables: binary, nominal, and ordinal. Binary are, for example, the yes-no outcomes. Nominal variables represent groups with no order, no rank between them, like for example colors, and ordinal variables represent groups that are ranked in a specific order, like for example the finishing place in a race. In a dataset, we can find a combination of different variables. Here you can see categorical binomial, quantitative discrete, categorical nominal, etc. So it's important that you understand that you can work with datasets which are heterogeneous in terms of its variables. Well, now we are going to focus a little bit more on descriptive statistics. The main use of descriptive statistics obviously will be to describe the data. I'm pretty sure that you have seen summary statistics in many fields, and they are good examples of descriptive statistics. Each individual variable can be described using descriptive statistics. This is what we call univariate analysis. The most generic tools used in descriptive statistics are frequencies, ranges, means, modes, medians, and standard deviations. Well, within descriptive statistics, we can find two main areas: the tools that measure a central tendency and the tool that measure variability. For central tendency, we have mean, mode, and median, while to measure of variability, we can use variance, range, and dispersion. Well, to start with statistical analysis, it's important that we know the way that data values are distributed within the dataset. The term measures of central tendency can sound a little bit grand, but basically what we are trying to know by using these measures is what the middle value in our data is. As I said, the most common measures of central tendency are mean, median, and mode. Okay, let's take a look at this student data, and in particular, we are going to explore the age of our students. Now, the youngest student in this sample is 22, and the oldest is 48. You can see that all the other ages are somewhere in between these extremes, and we should expect that a typical student age is somewhere in the middle of this range. So one value we can use to determine the middle of our data is the simple average, or the mean as it's more commonly referred to in statistics. Here you have the formula for calculating the mean for a full population of data. And note that in that case we are representing the mean with the Greek letter mu. However, we are dealing here with a sample of the data, not the whole population. So we write it like this, and we call the mean with x bar. Either way, what the formula is telling you to do is to add together all the individual data values and divide by the total number of data values that there are. So in that case, the ages total up to 166, and there are 6 ages in the sample, so we divide by 6 to get a mean age of around 27.67. Another way we can define the middle of the data is to calculate the median value. In other words, the value that is at the middle position if we sort our data in order. If there is an odd number of observations in the dataset, the median is the value of the one in the middle position, which you can find using this formula. For an even number of observations, as you can see in our case, you need to find the middle two values and take the average using this formula. In our case, n value is 6, so we find the middle two whose positions are n divided by 2. So position 3 and n divided by 2 plus 1, so position 4. So we have position 3 and position 4, and the average of 23 and 24 is 23.5. This is the median for the data that we are showing here. And finally, we can look at the mode, which is simply the value that occurs most frequently. In this case, there are two instances of students with the age of 23 and only one for every of the other values. So 23 is our mode. You can see here the representation of the mode. Now let's suppose that we had a few more observations and we create a histogram that shows the frequency of each age value. It might look like this, and you can see here that by definition mode has the highest frequency. You can see in that example that most of the data are grouped on the left side, but there are a number of high H's that's pulling the mean to the right. You can see that the distribution of the data forms a skewed curve, and in this case we describe it as being right skewed because there is a long tail to the right. Now let's take a look at another field in our dataset. Now we are going to focus here on grades. Now the mean grade in this example is 49, the median is 50, and the mode is also 50. Now you can note that these central measurements are much closer together than the ones for age, and they are much closer to the middle of the overall range of values. With more observation, we might end up with a distribution that looks like this. This time, the distribution forms a well-shaped curves with the most frequent values clustered in the middle and symmetric tails of reducing frequency as you get closer to the end of the range. This is what statistician terms a normal distribution, and it occurs naturally a lot of times when you have sufficient volumes of data. Okay, now we are going to explain the measure of variability. Basically, when you plot your data, you will find that the data values vary. But this variability can be quite changing, and sometimes the values will vary widely and other times they are quite close. The rationale behind this measure of variability is to quantify that variance in our data. Let's examine the distribution of some students' grades. Let's take, for example, this case, Caritran, who scored a grade of 73. That seems like a pretty good grade, but we need to compare it to her fellow students to get a sense of how well she has actually done in her course. Maybe the course was easy and most students actually scored 90 or even more, and in that case, Carrie is among the poorest performers. Well, one thing that we can in order to find out it is to rank the grades into percentiles. This will tell us where a given grade lies in the distribution compared to all the other grades that were achieved in the same class. Here you can see that Carrie's grade is in the 80 percentile. So it means that she scored a higher grade than 80% of other students. Often, instead of using individual percentiles, we divide the data distribution into quartiles that indicates the boundaries for 25%, 50%, 75%, and 100. Often, we visualize the quartiles of the distribution using a box and whiskers chart, in which the box shows the inner two quartiles from 25 to 75%, with a line showing the 50% boundary, and the whiskers extend to include the first and the fourth quartiles, as you can see the representation here. Now note that the 50% boundary is actually the median of the distribution. Box and whiskers plot can be shown in either orientation, so it's very common to see them plotted vertically like you can see here. Now we are going to introduce an important concept, the concept of variance. The variance in a distribution determines how far from the mean the values and the distribution vary. For example, maybe most of our student grades are grouped together around the mean, with only a few grades in the first and fourth quartiles, or maybe the values are more evenly distributed across the entire range with only a small peak at the mean. We measure variance at the average square difference of the values in the dataset from the mean. We need to square the difference, otherwise the average difference from the mean will just be 0. Now, when we are working with a full population of data, we use the Greek letter sigma square to indicate the variance, and we calculate it using this formula. When we are working with a sample, we call the variance S square, and we calculate it slightly differently to allow for bias in the sample. Across a squared value means that the variance is not the same unit of measurement as our data, so we typically take the square root of the variance to calculate something that we call a standard deviation. The standard deviation gives us a fixed unit of measurement from the mean that we can use to determine how much variance there is in the data. And finally, we are going to talk a little bit about dispersion of the data. In a normal distribution, 68.26% of the data is within one standard deviation plus or minus of the mean. The 95.45% of the data is between 3 standard deviations. So here you can see again Carrie's grade of 73. We can use the standard deviation to measure how far this varies from the mean by calculating what's called a set score, using the appropriate formula for the full population or sample. In this case, Carrie's score is around 1.3 standard deviation above the mean. And well, here you have some final conclusions for this session. The first one is that vector, matrices, and linear algebra are in the foundations of data science. We can distinguish two main areas in statistics for data science, which are descriptive statistics and inferential statistics. In that session, we have been covering descriptive statistics, and next week we will be talking about inferential statistics. Also, you understand now that it's important to identify which types of variables we are working with in order to choose the appropriate statistical test, statistical methods, and read the results correctly. Then we have been talking about descriptive statistics that basically describe the data by following two main approaches: the measures to understand the central tendency and measures of variability. And we have been covering which are the more generally used descriptive statistics, which are range, frequencies, means, modes, medians, and standard deviations. That's all from me, guys. Thank you for your attention. I'll see you in our synchronous session. Goodbye.